This is the BrainChip podcast. Hear from our thought leaders about neuromorphic computing, beneficial AI, and how BrainChip's Akida is pushing AI to the edge. This podcast is a place for investors, practitioners, and anyone interested in the future of AI.
Good day, everyone. Thank you for joining us with this podcast. We have the pleasure today of having Anil Mankar, who is our second founder. We spoke to Peter Vandermeer last time. Anil is the chip in BrainChip. He's been with the company since its inception. Anil, maybe take a moment, just introduce yourself, and then I'll ask a few questions and we'll go back and forth and we'll see how this thing goes.
Yeah, thanks, Lou. Yeah, so my name is Anil Mankar, and I have been with this company, as Lou said, since 2013 when I met Peter. So I spent most of my life in semiconductor industry. So when I met Peter and he showed me how the spikes were learning, I saw an opportunity to really combine my semiconductor experience with the biology that Peter has studied. And now you saw, as they say, rest is history, right? So we have BrainChip, Akida. We can talk about that as we go, Lou.
Yeah, can you talk a little bit about, as we position the company to beneficial AI, a little bit about how and which markets that we can take advantage of or provide that beneficial AI to?
Yeah, so the beneficial AI basically means for humankind and other things, right? So if you look at some of the applications that we have come up with, and the best thing I like about is the robot can see, hear, taste, smell, and feel. So those kind of applications which are very well suited to run on Akida, either in SNN mode or CNN mode, they can actually go into the next sensor and be in a healthcare environment where you can do breath analysis, or even being low power can really conserve energy. So those are the main application that we think can come out of Akida application. And this all is possible because we can be in the IoT device, we can be close to the where sensor is, and we can actually do the analysis at the sensor. So rather than sending all of this data all the way back to the cloud, which consumes a lot of bandwidth and power and other things, we can actually do analytics at the edge, sometimes in healthcare field by doing some breath analyzer, or other places where industrial IoT. So all of this is going to reduce the total power consumption and the carbon footprint. So that's kind of a beneficial AI, good for the humankind application that Akida can bring in.
Can you talk a little bit, Peter did on our last podcast, a little bit about what we mean when we talk about the event domain and neuromorphic computing in particular, the difference between neuromorphic and a standard von Neumann architecture as it relates to us being able to work at the edge?
Very good. I think the neuromorphic compute basically is quite different than von Neumann architecture, where the CPU, memory, and the program that's running, and it's very deterministic. While neuromorphic, the way it copies what our brain does, and brain actually communicates in a spatio-temporal integration of spike events, which we call events also. So all the information, whether it's vision or audio or smell or taste, it's all, the compute element is exactly the same. There are a bunch of synapses connected to a neuron, and as the spikes come in, the neurons that can see the repeating patterns can learn from it. So neuromorphic computation means mimic just the same way that our brain computes. So that's what we call our Akida is the biologically inspired, but digitally engineered, right? Because it's all digital design. Now, there are people who have done a neuromorphic computation after it started with Clever Mead looking at the transistor saying, hey, this looks like what a brain, a neuron is doing, integrating lots of information. But that was analog. When I met Peter, we wanted to make sure that everything is digital. And also by not just mimicking the integration of spikes, we also went one step further to really do event domain convolutions and even event domain functions that a standard CNN will do. So our implementation of neural computation goes one step beyond what the standard neuromorphic thing that you might see. And the reason for that is once we actually implemented in digital logic what we call Snap 64, that was our first product, which we could learn, we could really do native SNN. But we realized that while the native SNN algorithms were still coming along, there was a lot of application for deep neural networks where it was all extracting features and all that. So we wanted an architecture that can solve today's problem, take the CNN, bring them into event domains so we take advantage of the low power, and also do native SNN. So that's where we actually were very happy to Akida architecture came because of that, because we just didn't want to do neuromorphic computation just to mimic brain, but we went one step further in terms of doing in event domain convolutions, and that's why we are so efficient in either solving CNN problem, but bring them into event domain. And of course, there are some applications that can be directly encoded into event domain itself. So we are at least a generation ahead of just a standard neuromorphic computation because of the efficiency of the hardware and all the software that comes around it.
Now, could you, in layman's terms, describe a little bit when, I believe when laymen think about how we train a network, that you take, you take many pictures of something that you want to recognize. In neuromorphic computing, that's my understanding, not what we do. We extract features, and that allows us, as we demonstrate in many of our videos or our demonstrations, that you could take the tiger video, for example, and it doesn't matter what orientation the tiger is. We've extracted, or Akida has extracted, features, lines, curved lines, straight lines, transitions, transitions in intensity. Is that fundamentally what allows Akida to be one-shot learning and in many respects learn at the edge rather than simply train at the edge?
Okay, so there are two ways we can do that. Now, CNNs are extremely good at extracting features. So what Akida does is, if you had a CNN like MobileNet, which is doing object classification, the features were extracted by having hundreds of thousands of tiger samples and all that, and they extracted the feature, and that was able to do classification of other things. By taking that CNN into event domain, we actually preserved those features. We don't have to retrain them. And now the Akida, because the network was converted into event domain, Akida is actually able to have a different combinations of those features to really start classifying in the last layer. So there are two, either we keep the feature that way in CNN, but now one-shot learning after the network has been converted, we replace the last layer with Akida learning. And now a one-shot learning, when you see the new object, as long as it's a combination of the feature that we already extracted, we add a new object to this on the device. That's one way to learn. The second way to learn is directly encoding data that's coming in. That's like we do for our smell detection, COVID detection network, which is time series data. We can encode the data directly into event domain. And then by repeating pattern, we can actually learn a small network which is fully connected. So there are two ways to really extract feature, either directly from the events by just repeating the pattern and labeling it, or preserving the feature that way in CNN. So that's where we are unique in terms of our learning, and of course how we preserve the features. So one-shot learning happens because we actually, our neurons learn from repeating spikes coming in.
Can you comment a little bit? Akida is a hardware device, and BrainChip defines our mission in life. But can you kind of talk a little bit about the balance between what we do in hardware and all of the software support that's really required?
Which is a very good question. So most of the people who design neuromorphic computation, for them the software simulation was the afterthought. Not so for us. When we started designing Akida architecture, we knew we had to go from CNNs and into SNN, and also have a native thing. So our what we call a Akida development environment or a Meta TF, we actually do a complete simulator. We actually give all the software tools, and we start with a network that was defined in TensorFlow chaos, which is everybody understands it. So we maintain the software compatibility. So when our customers come to us, we're starting with the software simulator, the framework that they are already familiar with, which is TensorFlow chaos, and the network that they are already trained. They don't have to learn a new language. We actually take that, and then our tools that we develop, which is the chip simulator and CNN to SNN converter, they're all compatible to industry standard TensorFlow KOS, and that allows them to convert easily their network into a event domain. And once it's converted to event domain, the second thing that we do is the runtime software that we have that actually programs each bit in Akida, so that our customers do not have to know the complexities of the neuromorphic bits and bytes and how the learning thing happens. We all convert it directly by runtime software, and depending on the network description, the number of bits and all that, the runtime software that manages the complete network, and all the customers have to do is bring their network, bring their data set. After conversion to a tool, the runtime software runs in on the hardware and gives you results back. So there has been a lot of effort that last 2 years, our team in Toulouse and India, all the software guys, we have more software guys than hardware right now, to tell you frankly, to make a one-stop shop. And that architecture we actually use for new architecture exploration also.
So without going too much into the weeds in technical detail, I think it's clear to everyone that knows the company that our target is edge applications. Maybe just a couple of words on how it is that sparsity and quantization allow us to achieve ultra low power, and a couple of the use cases where the company's seen success.
Very good. So I think because we do this competition in spikes, when there are no spikes, there is no competition required. Typically, when people do for inference matrix multiplication, things like that, they do not know where the geos might be. But our event domain thing actually takes into account the inherent sparsity that already exists in the data set. Something like a 3D point cloud. Most of the third dimension points are very sparse, or a LiDAR data set. So what we have seen is when the networks are designed to process the 3D point cloud, we seen the sparsity anywhere between 60% to 90%. And more sparse the data is that's coming in that you're trying to analyze, the lower the number of computation that we see. That's why the power is low. So you're taking inherent advantage of the inherent sparsity in the data set is what allows us to be able to really do this analytics at the edge device. And typically, in the edge device, most of the sensor data that you are analyzing are very low speed sensor, like pressure, temperature, humidity sensors, or even audio sensor, which is kilohertz samples. So they can really run at a very low speed and very low power. So because of the neuromorphic nature and the event domain architecture that we chose for Akida, we are able to take the network that people cannot fit into the small size, the memory bandwidth, and compute power budget of the IoT device. We make it possible for people to run their algorithm as it is without any changes, but we can make it run on the IoT device because of the low power nature, sparsity of the data, and of course the on-chip learning, one-shot learning is the icing on the cake, because you don't have to go back to the cloud, retrain the network when you want to just add a couple of objects or a couple of voice command to your remote control.
I forget, maybe it was a month ago or so, you did a talk at the AI Field Day. Subsequently, I did a podcast with them. Maybe we could give listeners directions as to how to go to see what you did at the AI Field Day, which I thought was very impressive, and many of those attendees kind of echoed that thought, and then we can kind of wrap up.
Yeah, actually, yeah, that AI field day presentation was very good. All the experts from the industry were there, and they were really impressed with the one-shot learning demo. All those demos are available. They were recorded at brainchip.com/videos, and there are snippets of different examples. There are some all the what I talked about, robot seeing all the five senses. Those networks are there. The presentation is there. The question and answer session also doing that thing also recorded. So you can definitely see it on our website or YouTube links that are there for brainchipping.com videos.
Yeah, very good. So for all of our listeners, we have a very active LinkedIn page. We have a very active Twitter feed. We have a YouTube channel. We've had these podcasts now. I think this may be our fourth. In our next, I expect that we will bring in a third party, an industry analyst or an editor. You get some third-party validation or third-party viewpoints on the AI market generally, and maybe more specifically the edge market. So I'd like to thank everyone for either listening or downloading, and we will talk again in about a month. Thank you very much.
Thank you very much.
Thanks for listening to the BrainChip podcast. Please remember to rate and review on your favorite podcast platform.